actually isn't. Oh, Christ.
This project was originally conceived as a curling design that could be manufactured, moved via truck to a location, and deployed at the push of a button using a motor, inspired largely by Thomas Heatherwick's rolling bridge in Paddington Basin, London. The bridge would have practical applications in developing or disaster-afflicted areas, where a safe, reliable, effective route of transportation or evacuation could be established in a matter of minutes. This bridge would be available to the layman at low cost due to cheaper materials and simpler design constraints than other similar military bridges. We made significant progress as far as design goes, with few kinks left to work out before prototyping began. However, it was then proposed to us that we build a self-supporting reciprocal frame. The design we eventually settled on was a natural progression of a simple method used by Leonardo da Vinci known as a reciprocal frame, in which a bridge made up of several H-shaped sections rested upon one another so that each H-frame is supported by an adjacent H-frame, a self-supporting structure. This design, with divots at exactly calculated positions at a selected angle of 15 degrees on a member 2 feet in length in the frame, ended up being our final design.
Manufacture was simple. We scaled up our prototype designs, which we had laser cut, then we exported it to the 3-axis CNC for computer numerical control router in the shop, which cut it from a 48-inch by 43-inch sheet of CDX grade plywood. We then jigsawed the pieces free, routed them to remove excess material, and assembled the bridge. We also had at our disposal 9 3-foot lengths of 2x4 hemlock fir wood. We ended up using 6. We selected CDX plywood for 2 primary reasons. Firstly, it was available as surplus wood in good quantities in the school wood shop, which reduced the cost to manufacture. Furthermore, even though it does not look as good as A-level plywood, it was strong enough to carry the loads that we needed it to, as it was designed for exterior-grade housework. We used technology available to us in the MTHS shop when we were assembling the bridge. We used the shop-bought CNC again for computer numerical control 3-axis router. We used 2 jigsaws and a table router. Note that none of these technologies are necessarily required. Anyone with a power drill, a hand saw, and some patience could assemble a reciprocal frame of this design on their own, provided they had the materials. An even simpler design could be produced for even less, perhaps even just with sandpaper and several liters of elbow grease. The bridge was just as successful as we hoped it would be. It successfully held Alex's weight, and friction between the members and the beam mean we did not have to glue the beam to the members, making storage much easier. Given more time, we could easily determine exactly how much weight our bridge could hold at a maximum. At a minimum, we know it holds about 220 pounds. For this bridge's weight of about 22 pounds, this comes out to an efficiency of about 10. In general, we did what we set out to do. We created a bridge that is simple to manufacture and set up, and although that did not happen at the push of a button, the ease with which the bridge can be deployed means that the bridge is as simple to use as if it were at the push of a button. Future knowledge would likely be the specific gauging of the capabilities of the bridge, which would require manufacture of 1 or more spans for destructive testing, an endeavor that we did not have the time to accomplish. We could also gauge the strength of the bridge with and without wood glue or screws. There are also several ideas that we did not have to implement due to time constraints, such as 3D printed feet to increase support and stability at several possible bridge angles. Beyond that, the next logical step is expansion, by reducing the angle between the members or expanding the length of the members themselves.
I'm pretty sure that music's copyrighted.